This is Timothy Wood with Citadel Civil Engineering. This is CIVL202 statics, and in this video, we're going to continue our discussion of concurrent equations of equilibrium, and specifically, we're going to focus on free body diagrams. If we recall our procedure from last time, our procedure for tackling problems in equilibrium was to draw a free body diagram, from that free body diagram to write our equations of equilibrium, and then lastly to solve for that equation. So the first step is going to be to draw our free body diagram. In order to draw it, we need to know what it is. And basically this is going to be a sketch. So we're looking at reality, we're generating a mental model, and then we're going to share that mental model through a picture or a sketch. It's a sketch of an isolated body. This is what we mean by the free part. We're looking at the body all by itself with nothing else going on around it. And then we're looking at the external forces acting on that body. So the idea here is that we're going to draw the body itself, and then we're going to look at all the external forces that are acting on it so that the body's not touching anything. It just has the stuff that's pushing and pulling on it. When we think about these external forces, there's three classes of external forces that we might talk about. The things that would push and pull on a body. We might have body forces. Body forces are typically forces associated with the mass. So it's associated with the mass. In this case, we're typically talking about weight as civil engineers. Our electrical engineers might be thinking about electromagnetic forces between different bodies. Totally cool. That'd be a body force. We're not going to do that in this class. So we're just talking about weight. That's its own special class, body forces. Forces associated with the mass. Then we can also talk about loads. And loads are typically our applied forces or our design requirements. When we think of our design requirements, so forgive me for my civil engineering example, but let's say that we're designing the floor of the room that you're currently in. I'm assuming you're in a room. If not, picture yourself in a room. We might need to design the floor, and so we'd want to think about all the things that might push on the floor that we want them to stay in place. And so typically a floor will need to carry furniture and people and its own weight, although technically its own weight is a body force. All of these are going to be loads applied to the floor itself. And so when we're doing this sort of analysis, we need to figure out what these design requirements are. And those are going to be our loads that go onto the system. The last external force class we might have would be our reactions. We're going to abbreviate reactions RXN, and our reactions are going to be forces from a support or condition or connection. So this is where our body touches the outside world, and this is what maintains equilibrium. So again, if we're thinking about that floor, we're going to have reactions coming from the beams or the columns or the foundations underneath the floor. And so those things are pushing back up as the body force, the weight, and whatever applied loads are pushing down. So loads typically gravity-based, push down, reactions push back up. Doesn't necessarily have to be those directions. Typically what you're looking at is the differences are loads are the things that we're applying to the structure. The reactions are the connections. It's the forces generated by the connections to maintain that equilibrium, to keep things from moving. So typically what we'll do is we'll see our loads get applied, and then our reactions come from our supports. So these are our three major external loads. So now Let's talk about our free body diagram procedure. We'd like a good acronym. We are at a military college, so clearly I'm working on my summer beard. So I'm going to use the acronym BEARD to help me remember all the pieces that need to go into a free body diagram. So BEARD, this is my mnemonic memory aid. So the first thing that we're going to need to draw is the body itself. B stands for body. And so let's draw a picture. I've got a mug hanging from a rope. This is the system that I want to draw. And I want to just draw a quick free body diagram of this mug hanging from the rope. So the first thing I need to draw is the body. I think the body in this case is the mug itself. We'll remember that we're going to model this as a particle. So we're going to put on our fancy French hat, keep the pinky up. I'm an amazing artist. I know y'all are all excited to watch this video. I'm going to label it so that it's clear. There's my mug. So there's my body. Now the next thing that I'm going to draw is my external applied loads. So we can think specifically about our body forces and our loads. So if we look at our mug, we might say, well, does it have a mass? Yes, it has mass. It has mass. And when I think about the mass going on here, does it generate a force? Well, yes, it does. It generates weight. So gravity generates weight. We might say mass times gravity. And so that points downward. So that's a force pointing downward. I might label it with a capital W. This is one of those body forces. Other applied loads, like let's say that I had put something inside my mug, that might go up here. The weight of that might go up here. Those would be applied loads. The next thing I want to do, so that's B's for body, E's for external applied loads. A is for my axes. Okay, and so we're going to always need a coordinate system so that we know what we're doing. And so we might use an XY coordinate system like so, Cartesian coordinate system. Here I've drawn it with the origin basically at my particle. That often makes sense, but there's no problem if you want to draw it off to the side like so. That would show X, Y, and Z. Ooh, Z is looking rotated. We'll save that for later. Moments coming. Not right now, but coming. There's our coordinate system. We can draw it either way, and that works just fine. So there's our axes. So now we know what's going on there. R is our reactions. So now what we need to do is we need to look at the system, look where the system connects to the exterior, the outside world, and model that as a force. And so in this case, I have my mug. And where does the mug come in contact with the outside force? Well, it comes into contact through this rope. Now, we said that ropes, we pull on them, they go into tension. Don't push a rope, it's a bad plan. So we pull on it, which means the force is going to be along the line. We now know that we can use the position vector to find the unit vector to figure out the force along a line. In this case, it's pretty easy. The force just points up. So in this particular example, I can come over here and draw a tension force pointing straight up. Maybe I use a capital F to indicate force, and T is for tension. The last thing that we'd want to do is identify our dimensions and labels. W, F sub T. I've got some dimensions or some labels on there. Dimensions don't matter too much in this case. There's no angles going on. That might be something we'd have to watch out for. But if I have this, I've got my full beard. Everybody likes a good full beard, so we need our body, our external applied load, axes, reactions, dimensions, and labels. So this would give us our full free body diagram. In this example, all we've done is the mug hanging from a weight, like so. Mug hanging from a cable. There'll be others that we'll do in class or on the lecture together.